Hello, this is Meela Mitra from Space, and I have with us here today our special guest, Dr. Paul Rosen from JPL, and Achal Tandon, who's my co-host, and she's also from Space. She's educator in charge. So today we are here to talk to Dr. Rosen, and we are celebrating. This is part of the broad celebration that we are joining in for World Space Week. So World Space Week is on October 4th to 10th, organized by the UN every year. And Space is celebrating it throughout this month of October and celebrating the theme this time, which is remote sensing. So we have on board our special guest who will talk to us about remote sensing and a specific project. Let me first say hello, Dr. Rosen. Welcome here today.
Thank you. Good morning to everyone in India.
And hello, Achal.
Hello,
welcome.
How are you?
Thanks. So we are so happy to have here with us today Dr. Paul Rosen. Dr. Rosen is currently project scientist for the NASA-ISRO Synthetic Aperture Radar mission, known popularly as NISAR, at the Jet Propulsion Lab. From 2006 to 2012, he was the manager of the Radar Science and Engineering section. His assignments at JPL have centered on scientific and engineering research and development of radar instruments and applications, particularly in the area of SAR, synthetic aperture radar, interferometry. He was a team leader on the shuttle radar topography mission, for which he received NASA's Exceptional Service Medal in 2001, National Achievement Medal in 2002. Prior to JPL, Dr. Rosen spent 2 years at Kanazawa University in Japan, propagation in the ionosphere. So I'll take it forward to Dr. Rosen now. And recently, some of us were lucky to attend a NISAR interaction where you talked about NISAR, and today we're looking forward to hearing from you about NISAR and synthetic aperture radar. So please tell us a little more, and then maybe you can show us a presentation or something so we can find out a little more about it.
Sure. Yeah. Well, again, good morning, everyone. It's a pleasure to be speaking with you today. NISAR is a mission that we've been working on with the Indian Space Research Organization for around 4 years now. It takes a long time to reach an agreement between two space agencies and two governments to work on such a huge project as NISAR. But finally, about 2 years ago, we made the agreement, and for the past 2 years, we've been working technically together to build what I'm going to show you in my presentation today. It's focused on Earth science and on applications that are of great benefit to society. But first, I'm going to show you a little bit about the mission, a little bit about the technology that we are using, and then a little bit about how important the applications are.
Yeah, we have I don't know, Dr. Rosen, if you can see the number of viewers down there. As the host, I can, but for each viewer that's logged in, we have a whole classroom or auditorium full of students who are watching us. So both of you should be aware that we have a whole bunch of students sitting and watching us.
Well, how many people are signed in do you see? I can't see that.
So I can see about 20 people signed in, and I know each of them is a classroom. So we have, at least 20 times 50, at least.
Wow, well, that's great. Please study very hard. Go into a technical field like engineering so that we can take best advantage of the data from this mission as well as from future missions that hopefully you will be building with ISRO in the future.
And what is the timeline for the NISAR mission? I don't know if you'll show it, but in your presentation, but when is the expected launch for it?
The expected launch is sometime around the end of 2020 or 2020, somewhere in 2020. Technical developments are quite complicated. We have to build all of the pieces specially from scratch, basically, because there's only one of these missions and only one that does this kind of thing. It takes a long time to build it, and especially when you have two partners doing substantial amounts of work on two different sides of the Pacific Ocean, 12 and a half hours a day. It takes a lot of coordination and a lot of checking, because once you launch something into space, of course, you can't go up and fix it. So it has to work through the launch, and then after you deploy it and operate it, it has to live throughout its life cycle and work. So it takes a lot of careful design, development, and testing in order to get these things to launch and succeed.
Right. Yeah, it's interesting when two countries are collaborating. And again, I don't know if you'll address it maybe at the end, but I would like to ask you which parts are India doing and which parts are the US doing.
That's in the presentation. I can show you that. Yeah.
Okay. So yeah, we can go ahead and start because we have a lot of viewers online. Okay.
All right. So it's the green one, share screen. That's what I'm doing, right?
Yeah, that's right.
Or screen share, I should say. Entire screen. Maybe just that one. Let's try that.
Yes.
Okay, can you see? Let me go back to the beginning of this.
Right. We can see it. We can see your presentation. Yeah.
Okay, good. So this is a presentation I actually gave for another webinar. It was a webinar that was based in the United States, but people from around the country and perhaps around the world also saw this. Since we put together this Google Hangout so quickly, I didn't have a chance to put something else together, but I think that this is a nice representative presentation of NISAR and what it's all about. So I'm going to go forward with this. This talk is about twice as long as 20 minutes, but I'm going to skip over parts just to make it fit within the time allotted. So I'm going to touch on what a SAR radar measurement is and what the capabilities are, say a little bit about the mission that we're talking about, NISAR, talk about some of the science and applications objectives, and the potentials for humanitarian applications. And I'll just give a brief summary of these things so that we don't take too long. So I'm hoping that this video here will actually work. And this should try to illustrate for you what synthetic aperture radar is. So you can see we fly along. This is a satellite flying along, sending pulses of energy to the ground. This is radar energy. Those pulses come back and they illuminate the target on the ground, which is, in this case, the Earth. And as we fly along, we collect more and more pulses. And by using the frequency information in that signal, we can take the pulsed information, which is very low resolution, and add them all together and eventually create a full high-resolution image of the Earth, grayscale image of the Earth like that. So the synthetic aperture is this long duration in space that we use to illuminate a given target.
Dr. Rosen, can you try making it a full screen, just because it's coming a little blurred?
I can try, but I think the video didn't work the last time I tried that, but let's see what happens.
Okay, and if it doesn't work, we'll go back to.
Okay, so is that better?
Yeah, but can you do the slideshow? Do you want to try that?
You mean the movie?
No, in the presentation, if it's PPT, then you have a choice of view. Under view, there is a choice of slides.
Yeah, I
Or
did
under your
that.
slideshow.
This is slideshow right now.
Okay.
It's in slideshow
Okay.
mode on my screen. Yeah.
Okay. Yeah, so that's how it's showing. Yeah. Okay. Yeah, we can go ahead.
Okay, so synthetic aperture radar SAR, it operates at microwave wavelengths, just like perhaps you have a microwave oven in your house. So these are not the same kinds of signals that you see with your eyes. And here's an example of just how different a SAR image is from an optical image from space. This is a sand sheet in the desert of Africa, Sudan actually. And you can see the sand sheet in an optical image looks like what you would expect. It looks like sand. It doesn't have a lot of features. But in the middle here, you see a swath that was cut through by a radar, a synthetic aperture radar, operating at a long wavelength, 24 centimeters. So that's a very long wavelength, size of your hand or so. So what you're seeing here is not sand, but you're actually seeing through the sand, and you're seeing the reflection of the radar signal from the bedrock that's down below the sand. And what it looks like is river channels below the sand. These are ancient river channels that you're mapping with the SAR technique.
So I'm just going to stop you for a minute because I can see your presentation and Achal can, but somebody who's viewing on the YouTube is saying that they're not able to see it. So did you start seeing it and then you lost it? Okay, so you can't see him at all? So can you just close the presentation and restart it?
So close PowerPoint, you mean?
Yeah, close PowerPoint.
And restart PowerPoint?
Yeah.
And then reshare it?
And yeah, that's right.
Okay, now I have to find that presentation again. 1 second. It's going to take a minute.
Okay, sorry about that.
It's okay. Where did I put that? There it is. All right. Now you want me to go back here and share my screen. And should I share my whole screen or just share the PowerPoint? What should I do?
You can share the PowerPoint.
Okay. So there it's back. And I'll go into slideshow mode. There, now it should be back to where it was before.
Yeah.
Okay, so can I go forward?
Yeah, you can go to the fourth slide or wherever you were about.
Okay. So the point is that we can see something very much different from visible light with the L-band radar. What we're seeing is the structure of the surface, the electrical property and the structure of the surface, not the chemical properties that we tend to see with our eyes. We can also measure something called polarization, which you're familiar with from sunglasses, perhaps, where if the light is oriented in a particular way, the surface can pick out that particular light's orientation and tell you different things about the surface. So in this case, there's an image showing the streets of Los Angeles showing up as different colors due to their different orientation physically on the ground. And that we measure with polarization. The other thing we measure with this system is called the interferometric phase. This is a little bit of a difficult concept. I'm not exactly sure what level the students are that I'm speaking with. But yeah.
So one problem is that, again, they're not able to see the presentation. So I'm not sure why it's going away.
Well, let's see. If I go out like this, is that any better? I just
Uh,
take it out of screen mode.
no,
Can
then
you see
are you
me?
able to? Can you see him? Okay, so somehow we're losing you, I guess.
Hmm.
Oh, now you can see it. Yeah, so go ahead. We can see you now. Yeah, let's continue.
Okay.
Yeah,
So
yeah,
another
you can
thing
go
we
ahead.
measure. Okay, we measure the interferometric phase, and this is a fairly difficult concept to explain. Again, I don't know the level of the students, so let's just say that the phase, you can think of this as a water wave. The radio wave has peaks and it has troughs, and the phase is a measure of the distance from one peak to the next. So what we can use the measurement of the phase as a measure of distance. That in a variety of ways. Here's an example for topography where we have two radar images and the wave propagates just like a water wave, and it propagates from these two different SAR images and it will interfere with each other, and then we can measure the phase difference on a surface and create something called an interferogram. This interferogram then is a representation of the topography on the surface of the Earth. So we use interferometry to measure topography. We did this using the Shuttle Radar Topography mission back in the year 2000, where we had two antennas, one on the inside of the shuttle and one on the end of a mast. And we used that then to map the Earth's topography. If you have a smartphone, if you look on Google Maps or some other mapping application on your smartphone, the data you are using is from the SRTM mission. Here's a picture of India using the Landsat image mosaic. This is the radar image mosaic, and if I move this out of the way, since I don't think you can see what the topography of India looks like from the Shuttle Radar Topography mission. So that's one use of other use, which is what NISAR will measure, is deformation. And in this case, what we see is that we can measure the surface. Let me try going back into display mode because this is an animation. So hopefully you can see this. We have an observation from a spacecraft or an aircraft, and we measure the phase from the spacecraft to the ground. And then, so we can create an image with its phase from that. Then we fly over again a second time, and you notice here the ground has moved, and we measure extra phase here. And that extra phase allows us to measure, again, an interferogram. But in this case, instead of measuring topography, we're measuring the change in the topography. And we can measure that down to a millimeter of accuracy from space. So here you can see a signal from the ground that has actually sunk from one time to the next by 13 centimeters. And you can measure that from space. So, break out of this again and go back to this. So we measure the phase. We can measure the so-called decorrelation, that is where the phase doesn't really give us a good measurement. We can also measure that. And we can measure the polarization. These are our basic measurements that we're going to use for NISAR. So this is the NISAR mission.
So,
yes.
okay.
Go ahead.
No, yeah, go ahead. Yeah. It just takes some time to refresh, I guess. So it's fine. Yeah, it's a go.
Okay, I'll try to speak a little slower maybe to keep up.
No, that's fine. Yeah, it's just a slide.
Yeah, so this is the NISAR mission concept. It's a very big satellite, actually. This is 12 meters across with this reflector dish up here. 12 meters. That's a very large structure in space. This is 9 meters. This whole thing is around 5 meters. And you saw how the how the satellite flies along before and creates images. This system creates a swath that's 240 kilometers wide. So here are the basic characteristics for the mission. It has two wavelengths, L-band, like I mentioned before, 24 centimeter wavelength. The US is providing that radar. Then another radar, which is at half the wavelength, that's being provided by India. So we have actually two full instruments on this spacecraft, and US and India are both building a piece of it. It creates a very wide swath, 240 kilometers, and that allows us, using this wide swath, to create a full map of the Earth's land and ice surfaces every 12 days from two parts of the orbit, once we're going up and then when we're coming down. So really, we're sampling the Earth every 6 days, watching it change, using this interferometric and polarimetric technique to measure the motion and to measure the change in the forest cover. Our key characteristics are to look at ice, to look at hazards, deformation, to look at hazards of fires and things like that, and to look at vegetation. Those are the key measurements we're trying to make. And the key characteristics of this mission are that we have dense temporal and spatial sampling, comprehensive global measurements, and we also have the ability with these two unique radar systems to target new science with this. The other thing that is somewhat unique about this mission is that the US and India have agreed that all of the data will be freely and openly available to anyone around the world. So you can go to the ISRO or NASA archive and download all the products and process the data yourself for science. So I'm going to skip the next one. It's a little bit of a detail, and I think I'll skip this one too, which is also detail. So this addresses the work share. Let me put this in full screen mode. So again, this is the satellite. This big dish here is a gold-plated mesh. It only weighs about 100 kilograms, even though it's 12 meters in diameter. And it collapses to a very small package for the launch. That's provided by the US. This long boom here, it's called a boom, is also provided by the US. The spacecraft bus, the spacecraft that propels the satellite and controls its orientation, that's provided by ISRO. And the structure is built here by the US, but it has an L-band radar and an S-band radar on it. So one's provided by the US and one's provided by India. So you can see the different colors here illustrate what's provided by whom. So the spacecraft by India, S-band electronics by India, and a big factor is the launch vehicles provided by India. The GSLV Mark II is India's latest successful launch vehicle. The PSLV has been very successful. The GSLV now has 3 or 4, I think 3 launches that have been actually perfect for the last 3 launches. So it's a great launch vehicle to launch this. You can see from this chart that it's a very highly...
So Paul, again, we are not able to see you or the presentation. So
how about now? Is
so
that
you
better?
can see, yeah, I can see it now.
Okay, so I guess I should not go into full screen slideshow mode. You can't see that.
Yeah, maybe. Yeah.
Okay, so did you see any of this that I was explaining about the work share or not?
No, you can maybe, yeah, you can just repeat this slide.
Okay.
I can see it now.
Okay, so this shows the work share between the US and India, NASA and ISRO. And you can see those things marked red are the parts that are provided by ISRO, and the ones that are marked in green are those provided by the US. So the spacecraft, the S-band electronics, and the launch vehicle are all provided by ISRO. The rest of the structures and the L-band electronics and this big reflector are provided by NASA. So it's actually, in terms of the cost, in terms of the scale and scope of these various contributions, it's a very equal partnership, and it's a really enabling partnership. Neither of our countries feel we could have done a mission of this complexity without the other. It's a very important partnership. So, as I mentioned before, the mission is designed to take data in an unprecedented fashion. This is showing you the coverage that we get every 12 days. We take data on the ascending part of the orbit and on the descending part of the orbit, and we take it over all of the land and all of the ice surfaces and some coastal areas as well. So this is a huge amount of data. It's about 1 petabyte of raw data every year, which is actually a very large amount of data. And then when processed, it expands even further. But we need this kind of sampling in order to be able to track the changes that we're interested in. From a humanitarian point of view, SAR in general can answer a lot of different kinds of questions as an observational technology. So you can see on the left here a number of different challenges that the governments of the world are trying to address with remote sensing: food security, water availability, climate risk, and all these other things you see. SAR has been shown to be able to address many of these things. Just a few examples: for global food security, being able to measure soil moisture and to track the crop growth at the scale of agriculture is an important factor in understanding whether food will be available or not. Another interesting application is freshwater availability. I'll show you an example of how we can detect whether water is being pumped from below the ground or not. And that will then tell you whether fresh water could be available in the future. So many different applications that SAR can contribute to that help us to understand risks for people around the world. So let's see. This is a plot here of water resources, aquifers, places where water is being pumped from below the ground around the world. And these are these red marks to show you what the footprint of the aquifer, the size of the aquifer that can be supporting humans. And the larger one is the size of the actual usage of that aquifer. So you can see many aquifers are being overstressed. And being able to monitor that is an important thing. So here's an example of an aquifer in California that we have been monitoring using existing SAR data. And what you see here, this I hope you can see it, this is the color means how much the ground has sunk, subsided, over a period of 4 or 5 years. You can see it has sunk, the whole surface of the ground at many kilometer scale has sunk by 70 centimeters, almost 1 meter, in that 5-year period. And that's because people are pulling water from below the surface, watering the fields. That water then doesn't make it back down into the subsurface, and so the ground is sinking. And potentially cannot sustain new water in the future when it rains. So it's a very important problem, and this is happening all over the world. Here's another example of aquifer usage. This is in the Los Angeles Basin. This is another animation, so I hope you'll be able to see it. Let me try it, and you should be able to see the colors changing, going from blue and magenta up through orange and red. Let's see if it actually works. It seems kind of stuck there. You can see what's labeled on there are the earthquake faults in the Los Angeles area. So what you're seeing is the Los Angeles Basin with millions or hundreds of thousands of houses and businesses going up and down by about 2 centimeters every year as we pump water out from below the ground in the summertime and then pump it back in the wintertime to recharge it. So this is the Earth breathing, and we can measure this using a system like NISAR, not just in the Los Angeles Basin where it happens to work, but all over the Earth where we'll be able to take these data. Very powerful technique for measuring very small changes of the Earth's surface. The other thing we can do is measure hazards. So here's an example of a measurement, again, from another SAR satellite that actually is not operating anymore, looking at the change due to an earthquake. So the earthquake occurred in New Zealand back in 2011, and we collected a radar image shortly after that. There happened to be one before the earthquake as well, and we could take the difference of those two images and create this map here in the middle that I'm putting my cursor on that we call a damage proxy map. And that means that it's telling us where we believe the surface was damaged. Maybe buildings fell down or something like that. So this was within a day of the actual earthquake. 4 months later, and then again 8 months after that, the people on the ground were mapping where they thought the damage occurred. And it wasn't until 8 months after the actual earthquake that they could start to get a picture of damage that was similar to what we measured in 1 day with the radar. And I actually think perhaps ours was a little more accurate than the map that they put together. And with a data system and a data set like NISAR will produce, where we're taking 6 days effectively, we should be able to respond to disasters very quickly and help people to understand where damage occurred and where best to deploy resources. For the Nepal earthquake, we performed a similar analysis. You can see this is a timeline that's very similar with some of the products. And we were able, in this case, to show that by providing this map that you see on the left and the detail of that map shown on the right, each of these areas here is a town in Nepal or a village that has sustained some sort of damage. And we provided this information to other space agencies, and they actually used it to direct their satellites that operate at higher resolution to look for damage. And most of the time we were correct. They were very, very appreciative of having this method for looking for damage so quickly. And this again was with an international SAR satellite, not NISAR. When NISAR is flying, it will be an extremely important addition to the international constellation of satellites. Reliable data that will allow us to make these kinds of measurements throughout the life of the mission. So I know that's taken a lot of time and we've had some problems with the technology, but I'll just summarize quickly, saying that the mission it's a new partnership. It's the biggest partnership ever between NASA and ISRO. It's a very exciting partnership. It's scheduled for launch, like I said, in late 2020. It may slip into 2021. We have used the international constellation of SAR satellites to demonstrate the potential of SAR for humanitarian applications. And we think NISAR will be quite unique in its characteristics and will have a major additional benefit for humanitarian efforts. as well as science. I didn't talk very much about the science in this talk, but there's a lot of important science objectives in climate change, hazard management, ice dynamics, earthquake physics, sea ice tracking, and ecosystems carbon, that all of that is a major science focus of this mission. And if we can talk about that in the question and answer period if you're interested. So that's my presentation.
Yes, thanks, Dr. Rosen. That was very informative. And now I'll take it over to Achal. Maybe she has some questions. Yeah, Achal? Do you have any questions, Achal, that we can bring forward? Is your, please check your microphone.
Yeah, now, am I audible now?
Yeah, you're fine. Go ahead.
Yeah, all right. So, so I have questions with me. So the first question is that what are the probabilities of so much data being shared with the interested candidates?
What do you mean interested candidates? What does that mean?
Like the ones who are like really want to know what is happening with NISAR, like the SAR event, and what are we doing, what kind of data is coming from that. Those who want to take each and every step, they want to see what is happening with that event and what are the data we are downloading, those kind of things.
I see. So each of our agencies has a web page. You can see track the development of the satellites on the web page, and eventually we will have an interface once we're closer to launch that will show you what the acquisition plan is, where data will be available, in which radar mode, and there will be a way to basically click on a link to download whatever data you're interested in. The actual science data will be placed on an archive for the U.S. that happens to be up in Alaska. We already have much data up there that you can go and use right now. If you go to the Alaska Satellite Facility, asf.alaska.edu, you'll find an interface to a data system that is basically free and open. There's a lot of spaceborne and airborne data that have similar characteristics to what we're going to have for NISAR. And that will allow these students to learn and get used to using those kinds of data if they wanted to. That's where the NISAR data will end up. And the same kind of interface for selecting and downloading data will exist for NISAR at that time.
Right. So the second question is from Shivom. He's from space only. Now he's asking that how this technology is different from hyperspectral imaging.
That's a good question. I was just actually, 2 weeks ago, I was in Africa giving lectures with a colleague of mine on SAR for me, and he was talking about hyperspectral. So if you had been at those lectures, you would have seen exactly the difference. So it's let's see. The hyperspectral is not only optical wavelengths, but it's the wavelengths that are both at the lower part and the upper part of the optical wavelength spectrum. So you go from ultraviolet through the optical to the infrared. So a very broad spectrum of basically optical frequency light, very short wavelengths in the nanometer range. So tiny, tiny wavelengths that are mostly sensitive to the chemical properties of molecules. So you can measure the atmospheric molecule constituents, you can measure chlorophyll, you can measure all of the different parameters that are at the molecular level in remote sensing. Whereas the radar has a very long wavelength. It's literally this long in our case. And so we're not sensitive to things that are at the molecular level. We're sensitive to things that are at the, as we say, macroscopic level, like tree branches and rocks and people, cars, buildings, that kind of thing is what we're sensitive. So you see something very different, and you get very complementary information. Hyperspectral tells you about when it's not cloudy, of course. The hyperspectral tells you about the kinds of materials that are on the ground. The radar can see through the clouds and can see at night, but it tells you about the structure that's on the ground. Does that make sense?
All right.
Yeah, thanks.
Yeah. Thank you, sir. Sir, the next question is from Sean. He's from Indraprastha School, Dwarka. Now, he's asking that how is it possible to accurately report disastrous occurrences real time with NISAR?
So that's a good question. We can't really do it real time because we have to wait for the satellite to fly overhead to get the data. And it can be quite a while sometimes. That was one of the slides that I skipped. The probability of being able to see a given spot on the ground with NISAR over some number of days after an event can be in the 50 to 70% range. The probability of seeing it in real time is pretty close to zero because the event has to happen and then the satellite has to fly right overhead, and orbital mechanics doesn't allow that. So certainly for the kind of disasters where you need an instant response, like tsunami response and that kind of thing, you can't use a system like NISAR for that. However, after a major earthquake or during a flood event or during a fire event, these things can go on for a long time, and the cleanup effort, the discovery effort, can go on for weeks. So just by flying over within a day or 2 days after an event is a major help to be able to give a broad view of what's happening after a disaster. And, by the way, we also won't rely just on NISAR. We have the other international SAR satellites that we can all use. And so by the time NISAR is flying, there probably will be a dozen satellites of varying characteristics. Even if they don't get full coverage the way we do, they almost always will respond to a disaster. So they might have some data that can be applied and help us get data faster collectively than any one satellite.
And
Yeah.
I'll just chip in and ask, are these radar data correlated in some way, or is there a place where you can see all different radar data from different satellites in case of an earthquake or a tsunami or something, so that even if NISAR is not passing overhead, at least we have data from some satellite?
The way it usually works for disasters is that there's an international charter request, which is sent out to all of the space agencies. And they then will each create a set of data from their archives and from whatever is acquired, place it on a server that is then broadcast to the charter, a central clearinghouse. And everybody who subscribes to that central clearinghouse will then know where all the data is that's available. For NISAR's case, it's a little different because we're taking data everywhere all the time, and it's free and open. The data will simply be where it normally is. You just have to go and get it. It's slightly different.
Okay. All right, sir. So the next question is again from Shivam. He is asking that can we do soil mineral mapping with this technology?
Soil mineral mapping. So it's a little bit difficult to determine mineral types from just the structural and electrical properties that the star provides. You can do mineralogy much more easily with a hyperspectral system. Of course, there is no hyperspectral system in space right now, and for some reason, I'm not sure when they will launch one. And again, there's the issues with clouds and coverage and that kind of thing. So it's not the best technology. SAR is not the best technology for mineralogy. We don't measure things at the molecular level.
So, so the next question is from Suryansh Gupta from GD Goenka Rohini. He wants to ask, what new techniques are being used for disaster predictions and how will they be different from the older ones?
For disaster prediction. So that's a good question. Usually a good question means it's a difficult question to answer. So to be honest, I thought that the geodetic methods, the methods of measuring millimeter change from space using this interferometric technique is pretty innovative and pretty new relative to traditional methods. So my answer to that question is it's a combination of this new highly precise deformation measurement technique and the very high sampling rate that the system provides that allows us to track changes over time. Many satellites, especially SAR satellites, they acquire data in a not so regular fashion. So you cannot create long time series over large areas of the world. A lot of disasters don't occur in a predictable way. So if you have just, shall we say, haphazard or not so regular observations, it's really hard to model what those disasters are doing and then use that information to predict the future. It's our hope with this very regular observation technique that we have for NISAR that we can take a regular data set, see what's happening to the Earth as before a disaster occurs. We might not know a disaster is about to occur, but we can track what's going on the Earth. And after the disaster occurs, we can then go back and look and say, aha, there, we can see a signal that we should have been able to recognize and then apply that to future disaster prediction scenarios. That's part of the science we're trying to do.
Thank you for this answer. So the next question is from Vanshika. She's from Indraprastha School, Paschim Bihar. She's asking that how is NISAR different from other satellites?
Well, it's the very first satellite that has this kind of very large reflector radar on it. There's never been something quite like that before. The technology that we're using is brand new. It's the first satellite that's going to be in a free-flying orbit, meaning it's the first that's not on the space shuttle that has two radars on one platform. So that's brand new as well. It's the first international partnership of this nature between the US and India. That's brand new as well. And it's the first that's designed to address three specific science disciplines in this kind of a fashion. So that's new also. Almost everything about the system is actually new.
Better. So now this question is from Neeraj. He's from our Ludhiana office. He's asking that only for humanitarian purpose, or is it gonna aid military requirement of both the countries?
Well, I cannot say what ISRO will do with the data. Generally speaking, any system that is delivering free and open data is generally not considered to be a very great use to a military operation. But our resolution is not very high for this system, partly because we don't want the military to have any concerns about it, and partly because the science we're trying to accomplish does not require high-resolution data. The resolution is around, say, 10 meters for a given pixel, and by the time you do the processing to get a science product, it comes out to somewhere between 20 and 100 meter resolution. And generally speaking, the military is not interested in systems that have that kind of resolution. And in fact, it's a lot of data for us. Our goal is not looking at a particular place at high resolution. Our goal is to look at the whole Earth at low resolution so that we can see what's happening everywhere.
Okay, so the next question is from Aditya Singh from the Indian Heights School. He's asking that how can radar satellites provide an aid to disaster relief?
So I was trying to give some examples of that, but again, imagine a flood scenario. I know you have a lot of weather-related floods in India, coastal regions in particular. Usually when it's raining or there's a hurricane, it's quite cloudy. So optical satellites provide no means to see what's happening on the ground. Radar satellites can see through the clouds, they can see the ground, and they can see, especially if they're coming over the area every several days, you can measure what's changing in the ground. So it can be used for disaster monitoring and mitigation, and again, in deploying people and resources to help people who are stranded, it can help in that regard. Because a lot of these disasters cover very large areas, and it's hard to know where to go. Remote sensing systems help you with that. It can help with floods, fires, earthquakes. You don't have so many earthquakes in most of India, but you do have some earthquakes, and those kinds of disasters.
All right, sir. So next question is from Padma, and she is a student of St. John's Public School from Chennai. She wants to ask that what are the scientific concepts applied to NISAR?
Concepts applied to NISAR. The scientific, I'm not sure I understand the question. Meaning, what science will we do, or what concepts in science are used to create the mission? Applied to NISAR.
So maybe I think the science they are asking, since they are school students, they must be asking the science. I think concepts would be a little higher for them to understand right now.
Okay, so the science that we're trying to accomplish is basically three main science disciplines. One is in the area of the solid Earth. We're trying to measure the motion of the Earth down to millimeter and centimeter scale. So you can imagine painting a picture of the Earth, land surfaces, and then making that picture a motion picture where we're tracking the relative motion of all the plates of the Earth and all the volcanoes that are expanding and contracting, ground going up and down at the centimeter scale, making this motion picture over the life of the mission so that we can understand where the stress is building up in the plates, where it's relaxing, where plates are moving naturally with no stress building up and therefore relieving the probabilities of earthquakes, and tracking, again, the eruptions of volcanoes over the life of the mission so that we can understand the plumbing system of volcanoes and what leads to eruptions and what the risks are associated with over 800 active volcanoes around the Earth. So that is one of our science disciplines, understanding solid Earth physics in the crust of the Earth to understand hazards. Second one is understanding the motion of the Earth's ice sheets and sea ice, the so-called cryosphere. So Greenland and Antarctica have huge ice sheets with massive amounts of ice that are being formed every year from snowfall and being pushed out into the sea through the flow of the glaciers. What we're measuring with this mission is the velocity, the speed of those glaciers. All the glaciers in all the main ice sheets and in the mountain glaciers as well. So we can track how much ice is going out into the oceans. By combining that with a knowledge of how much snow is falling on the ice sheets, we can then estimate how much net mass is moving out to the water. When it goes from land to water, the ice then becomes water and it creates sea level rise. So what we're trying to understand is the physics of the motion of that ice so that we can understand the future of our climate and the implications for sea level rise. So that's the second main science objective. The third one is in ecosystem. And what we're trying to do is use the radar backscatter signal, the radar reflection, to measure how much woody biomass there is in the forests and in the savannas around the world, and how much it changes over the life of the mission. Because the amount of woody biomass determines the amount of carbon. The amount of carbon determines how much carbon dioxide goes up and down between the atmosphere, the ground, and the ocean. It's the biggest error source of our knowledge of carbon dioxide flux going from the ground to the air and back again that we have. So our mission is designed to measure that carbon flux to greater accuracy than any other mission. And by also doing that over the life of the mission, we can measure the disturbance due to people chopping down trees, regrowth, and disasters such as forest fires or hurricanes blowing trees down. We can measure all those things and understand the relative balance of human versus natural changes in our ecosystems. Those are the three principal science objectives.
All right, sir. So the next question is from BCM School, Ludhiana. From Punjab, there is a group of students who want to ask this question. Like, how remote sensing satellites detect earthquakes from that height?
So that's, I didn't have a chance to go through the details of the measurement technique, but it's almost magical. So the radar wavelength is about 24 centimeters, right? And I said the phase, where you are in the cycle of that wavelength, determines the distance. So we take two radar images, and for each pixel, we measure that phase. And the phase difference then we can measure down to a millimeter or two. So just by taking two images, taking the difference of those two images, we can get a phase difference which is accurate down to millimeters. Even though the satellite is 800 kilometers in space, you can measure the change in the surface down to a millimeter. So, and that change, if the ground moved, we'll measure it. If an earthquake occurs, the ground will move a lot, so we will measure that.
Right, sir.
Maybe a last question, Achal.
All right, now, so I have to choose out of a lot of questions now because students are asking a lot of questions, right? So this question, so this question is by some astronomer, J. Arun, from Babaji Vidyashram. So he's asking, won't it affect the humans by making them exposed to extra radiations?
That's a question that comes up a lot, and this is the way you can think about it. The amount of power that we are radiating out in space is something like, let's say, 1 kilowatt, and that's for about 40 microseconds. So the average power over time that we're radiating is something much less than a kilowatt. Say, let's just say about 100 watts. So you have a light bulb probably in your house, well, at least an old-fashioned light bulb, that has at least as much power as 100 watts. So that's what we're radiating. It's like a light bulb out in space. And the next point is that it's 800 kilometers away. And just as if you drop a pebble in the water, and the rings of the water propagate out and get bigger and bigger and bigger, and eventually the water wave amplitude just dissipates to practically nothing. When you are 800 kilometers away from a satellite, from a source of a light bulb, it's a very, very small amount of radiation, and the sun gives a lot more radiation than that. So yes, we are adding a little bit more radiation to the world, but it is a tiny, tiny amount of radiation.
All right. So, Mela, do I have the permission to ask some more questions?
I'm happy to answer a few more if that's okay.
So Achal, let's go for one more.
All
because
right.
I have a timing set for this. Yeah.
All right. So this is from Parvaroda. He's from Bal Bharati Public School. Now he's asking that how does this help to detect cyclones as these rays penetrate through air?
So that's a good question, and we hope with this system, with its wide swath and its fast repeat, that we can measure the onset of cyclones by looking at the oceans off the coasts of India. We're not looking at much of the Earth's oceans except around India. The Indian government wants to cover quite a bit of territory in the waters around India, specifically so that as the cyclones are being formed, they can track them coming in. What we measure is the roughness of the ocean surface as created by the winds from the cyclone. So at the onset of cyclone formation, the winds are relatively low and you don't see very much. But as the winds start to kick up more and more, the roughness of the surface of the ocean increases. And so by measuring this over a period of a day or so, we can use that to track the evolution of the cyclone and hopefully understand better what the likelihood that a cyclone will hit land or what its magnitude will grow to and that kind of thing. So yeah, it's something we really look forward to. There are other methods for measuring cyclones, but this one has good resolution and you can see it even through the clouds, so it gives you a lot more information.
Okay, let's go for another one, Achal.
All right, so I saw a question that what would be the duration of this mission? For how much time will it stay in the space and send us the information?
Another good question. So NASA has a policy to only plan a mission to last for 3 years. And the reason they do that is because they want to make sure that the science that's accomplished will have high impact. It doesn't mean that they plan to operate the mission for only 3 years. They just want it to succeed in 3 years. They're usually designed to last much more than 3 years, and this system has enough fuel on board. If all of the plans go according to plan, it could last as long as, it could take data as long as 22 years after the launch. It's not likely to last 22 years. Most satellites last between 5 and 10 in this class of satellites. So we're hoping for at least 5, and if we're lucky, we'll get 10.
Right. No. So over to you.
Okay, so Achal, do you want to ask one more?
Yeah, sure. The question is from Ashwin, 7th. He's from grade 7th, St. John's Public School, Chennai. He's asking what is the difference between S-band by India and L-band by NASA, which will be used in the satellite?
Another great question. So they're both going to be used. The L-band by NASA will be used over all of the Earth's surface. It will be used all of the land and ice surfaces. That's the, as we like to say, the workhorse instrument for meeting our global science objectives. The S-band instrument will be turned on at the same time as the L-band instrument, mostly over India and parts of Antarctica, because the Indian applications of greatest interest to ISRO are focused on India itself. So that's where they want to use the resources for the S-band system.
Achal, let's go ahead with the last question.
Okay, Mila. The next question is, the next question is from Samanvita Mahesh, and he's from like Indian High School, Dwarka. So the kid is asking that, can it detect underwater volcanic eruptions and other new living organisms on the seabed?
No, unfortunately, because we're looking at the electrical properties of the surface, microwaves don't penetrate through water. And basically, water looks kind of like a mirror to that. So we can't see anything below the water surface. And the microbes, again, those are microorganisms that are best suited to optical type or hyperspectral type measurements. So yeah, we can't see below the water, unfortunately. One small point about that is we can sometimes see on the surface of the water the expression of things below the water. So, for instance, if there is a channel where water will rush through below the surface of the water, sometimes the surface of the water is modulated by that channel, and we can measure that. But we can't really measure the deformation of the water or the microorganisms coming in. Can't do everything.
So, Dr. Rosen, do you have time for another few minutes? Because we're still getting in a lot of questions, then I'll just end it at 10:45.
10:45. Oh, that's...
so that's another, like, 8 minutes.
Oh, yeah, that's fine, because it's already 10 p.m. here, so 10:45
Right.
my time.
Yeah, just another 7-8 minutes.
No, it's fine for me. I also, before I forget, I just want to say to all of the students in Chennai, I'm going to be in Chennai on November 14th and 15th at IIT Madras. And I'm giving a talk on NISAR again at that time. So if you want to hear more about it and you happen to be free, it'll be the 15th in the evening, I think.
So Dr. Rosen, I'll take that information from you, and I'll forward it to all our schools in Chennai.
Okay, that sounds good.
Okay.
All right.
Achal?
Yeah.
Couple more.
Yeah. So, sir, the next question is from Shaurya Madan. He's again from GD Goenka School, Rohini, Delhi. So he's asking that what are the expectations from this collaboration, and does NASA plan to collaborate with ISRO for more projects in future, and are there any projects in pipeline which we are not aware of right now?
Yeah, this is a very good question also. The answer is yes, we have very, very high hopes for this partnership, both, I think, on the NASA side and the ISRO side. NASA, this is a huge partnership, and it has been enabling for this mission. So and it's a complex partnership. If we can show that we can put this mission together successfully, that it operates successfully, and that we still are friendly after building it, I think we have a lot of new possibilities. Somebody had asked questions about hyperspectral instruments earlier. We have discussions going on right now with ISRO about a possible hyperspectral satellite that we could do together. We already are helping ISRO with some of their Mars missions, and in the future we hope to have Mars mission collaborations with joint instruments on each other's platforms. We are collaborating in a field called scatterometry, which is kind of like SAR, but it's not quite as, it's mostly focused on ocean wind and cyclone tracking. So that one, India just recently launched their own satellite called StatSat to do this, but there are plans in the future for doing more scatterometers, and we're hoping for a partnership on that. And even in the area of SAR, we've already, now that our mission is going forward, we've talked about what's called the NISAR follow-on, or NISAR 2. Nobody has made any commitments, but we're starting to talk about whether it would make sense to keep this observation going over the next couple of decades. So yes, there's a lot of possibilities for the future. But again, it's a long time before we launch, and we need to make sure that everyone is happy with the way things are going. It turns out that India and the US have very different ways of doing business. And again, the 12.5 hours difference is also very challenging. So there's a lot of non-technical issues that we have to overcome, as well as many challenging technical issues. So
right.
It's an experiment.
So now let's go to the last question, Achal.
All right, sir. So the question is by Hardeep. He is one of the employees of space. So he wants to know that how are we going to use both the radars simultaneously?
Well, in a technical sense, there's a connection. There's a wire, basically, a timing signal that connects from the L-band system that NASA's providing to the S-band system. So we send, every time we are getting ready to send a pulse of energy at L-band, we send a timing signal to the S-band to say, okay, you need to send your pulse also right now. So they dance together. Each pulse goes out together. Because they're at different frequencies, they don't interfere with one another. And ISRO has taken great pains to design the system to match the L-band system. It's exactly the same swath, the same timing, and there's basically two independent radars when they're operating separately, but then when they are operating together, there's this timing signal that allows them to work together. I think that's what you meant by how. They are working together to get two frequency measurements to expand the dynamic range of observation, to get more fine-scale deformation and more fine-scale vegetation by using the S-band in combination with the L-band everywhere all the time. So NASA is relying primarily on the L-band for global observations.
Yeah, I think that was great. We got a lot of questions. We got to hear all about NISAR, and we're excited about India and US collaboration, as well as all the good that it's going to do on humanitarian grounds. So I would like to thank you for joining us here today, and we're excited to hear about your talk at Chennai, and we'll share that information with our schools in Chennai. And would you like to say anything at the end?
Well, I just want to say thank you for the opportunity, for allowing me to speak to you. It's great that there are so many students who are interested to hear me. I hope it was understandable. It's late at night here, so sometimes I get a little tired. But I just want to say it's been a real pleasure over the last 4 or 5 years to get to know so many colleagues from India, understand a little bit more about Indian culture, Indian food, which I love, and I've learned how to cook over the last 5 years. And just all of this friendships I've made over the years has really been great. So I look forward to continuing that over the next 5 years of development and 5 years of operations. Thank you.
So, and since you say you keep coming to India, we hope on behalf of Space to be able to invite you to interact with some of our students live at an occasion. So I'll talk to you later about that. But we're so grateful that you stayed up late and talked to all of us. And I'm sure Anchal had, just picked a few of the questions.
Yeah.
She had a lot of them. And sir, this
Yes.
whole thing is on YouTube, so we now have it on YouTube. And Anchal, do you have anything you would like to say at the end?
Yeah, I would really like to thank you, sir, for giving us the opportunity to interact with you and let us know a lot of things about the mission. And we hope that we are going to collaborate. You're going to collaborate with us, ISRO, with India, for more missions so that we can talk more about it and we
Sounds
can
great.
interact more. Yeah.
Sounds great.
Okay,
Thank you.
thank you, Dr. Rosen. Thank you, Anchal, for co-hosting, and thank you to all our
Thank you, ma'am.
students for joining in and being a part of this interaction today. Uh, Good afternoon, everybody. See you for our next hangout later. Thank you.
Yeah.
Bye bye.
Thank you, sir. Bye. Take care.